Okay. Hey y'all, I'm David and this is Lab 2 Projectile Motion. Okay, so for our intro, the purpose of this lab was one, to use the tracker to observe and record the position of our thrown projectile, which for us was a balled up piece of paper, and two, to create computational models that demonstrate the differences in our expected position with and without drag included. And the system for this lab was our paper ball, with the surroundings being the air and other objects just in the area. Our fundamental concepts were the position update formula, the velocity update formula, the force of drag, Newton's second law, and gravity, which is just a negative mg force vector in the y direction. Yeah. A preview of our results, the model that included drag was more closely aligned with our actual data than the model that didn't. Um, Okay, our initial conditions in the code, we just set the mass to the mass of our paper ball, set the initial position and velocity based on what they were at the very start of our video, and then set the time steps to the amount of time that it would skip every time you had a new observation point in the tracker. Our experimental procedure. So we pushed our balled up piece of paper off the table, which should be demonstrated here. Yep. And then we used the tracker app to track its location over the time of its descent, which gave us our X versus time graph on top and our Y versus time graph on the bottom. So for our code, uh, basically we calculated or our drag force. Um, and our coefficient of drag was 0.004, which we got through just guessing and checking until it looked mostly right. And then we calculated our net force and used our velocity and position update formulas. Yeah. So this is our trajectory graph. We have all three of them overlaid. The bottom orange line is our no drag model. The gray one is our drag model, and then the blue is our observed data. And as you can see, the one with drag more closely aligns with our observed data. Potential issues, there could be issues with the tracker. It does skip through time a little bit, and you're not clicking the exact same point on your ball every single time. We guess the B value, so it's not completely right. It's just an estimate. And outside interference, if there was a draft or something in the room, when you're using something as like small as a paper ball, that could make a big difference. Uh, do any of the models predict a terminal velocity? Yes, so here we have our velocity versus time without drag and with drag. As you can see, without drag, we have this constant acceleration. With drag, though, it starts to slow down and eventually it will taper off to one point, which would be the terminal velocity. What if the object was initially thrown straight up? So if it was initially thrown straight up with the same speed, it would take longer to reach the ground, because it would have to travel up, reach its peak, and then fall back down from a higher point than it would have initially. This equation demonstrates that. So as you can see, time is directly proportional to the initial velocity in the y direction. So if you throw up, it's gonna take longer to come down. Yeah, thank you.